Hola, mis estudiantes. We're going to do the condensed states of matter talk about solutions, solids, and liquids. I'm briefly going to remind you about the concept of IMFs and gases because it's really relevant in the first part of this discussion. So here's our gases review real quickly. Gases are mainly going to be our particles that have very little interaction with one another. They have no intermolecular forces, essentially. And the reason why is because the kinetic energy that they contain, their thermal energy right here, is overcoming the IMFs that they would experience if they were moving slower, having less kinetic energy. This is all explained by the kinetic molecular theory, and you can see that they approach ideal behavior at, think about it, is at high or low temperatures. Well, which one's making them move faster? It's got to be high. It's at high or low pressures. It's going to be one that doesn't crunch them together, so it's got to be low pressures. There we go. All right, ideal gases are gases with particles far apart from each other. They have high kinetic energy, allowing them to move very quickly, exerting no intermolecular forces. Their average kinetic energy is directly related to their Kelvin temperature. They're in constant motion, and the collisions of the particles with the walls of the container are the cause of the pressure exerted by the gas. It's not them colliding with each other, it's the fact that they are colliding with their chamber, which we measure the pressure of. The ideal gas law. Think about it in your head. You should be thinking PV equals nRT. Yay! And then now tell me the relationships. As pressure increases, you crunch your box of air down, the volume should decrease. So they're indirectly related. Pressure and temperature, as you increase the pressure, increase the temperature, what should happen to the pressure? Well, increasing temperature causes particles to move faster, colliding with the walls more often, which causes the pressure to therefore increase. Therefore, they are directly related. Volume and temperature. If you think about your little box of air, I know you're holding in your hands right now, your box of air, and you increase the temperature, or let's do it another way. Let's say decrease in the volume. If you decrease the volume, what should happen to the temperature? They're also going to start moving slower, hopefully. Moving slower means the temperature is decreased. Moving faster means the temperature is increased. The volume should therefore increase. And these are assuming all other constants, all other variables are constant. So you have to consider a couple of other things like constant pressure. So you've got to vary the changing temperature or changing volume in order to keep these other things constant as well. And these are all things that we can use whenever you're not given STP. When you're given STP, usually you can go, if you're trying to find moles, or you can, if you're trying to find moles, you can use Avogadro's law, or you can do a variety of other conversions. If you don't remember what STP is, it's 1 atmosphere and 273 degrees Kelvin, and then the gas should have a volume of 22.4 liters under these conditions. Here's your kinetic energy equation. What is R again? If it's energy, then R is going to be 8.31 joules per mole K. And you know that because of the constants given to you on your sheet, or you can actually look right here for the root mean square velocity. We call that URMs, and this is the square root of 3RT over M, where M is your molar mass in kilograms. That's one of the things that a lot of people forget. And there's your R constant again. The R in the previous law, the ideal gas law, is not this. It's 0.0821 atmosphere times liters per mole K. That's the one we usually choose to use, which means that all of our pressure units have to be in atmosphere, volume has to be in liters, and temperature has to be in Kelvin. It always has to be in Kelvin though for gases, so that's no difference among any of the equations. All right, the last bit here, you can see that the rate of effusion or diffusion, effusion is the escaping gas through a small pinhole. You can measure the speed or the velocity of these gases using this rate equation. And if you think back, you should remember that molar mass is going to influence the speed at which a gas can move if it's a heavier gas and it can't move as quickly. So your equation relates back to the molar masses of individual gases. This is rate 1 over rate 2 equals the molar mass of the square root of the molar mass of gas number 2 over the molar mass of gas number 1. So that shows the indirect relationship. Last ones here are the funny ones, the dirt over P one for your density. So your density is equal to dirt over P. molar mass is equal to dirt over P, and dirt is density. The density is always measured differently in gases. It's in grams per liter. And there's your dirt over P. Notice the R constant is the one with pressure, so the atmospheres. Last bit, high compressibility and low density just is a characteristic of gases, not of what we're going to talk about, which is your condensed states of matter. One more bit of review is your IMFs. So we just learned about these recently, but I really want to emphasize that London dispersion is present through all compounds and molecules, atoms even. So it is present. It is not the most important of all the IMFs. So it may not be the most important or the most significant interparticle attraction, but I still want you to know that, because on the AP exam last year, there was a problem with understanding that London dispersion can actually outweigh something if it's a much heavier molecule. We'll do some examples with these though. So I'll let you read through these and write down the highlighted parts if you need to. The few things that I've added here are the relative strengths. So hydrogen bonding is a very strong IMF, but it's very weak compared to our other bonds, which are intramolecular. So we still always have to know that intramolecular or particle attractions are very strong compared to IMFs or intermolecular forces. So the dipole-dipole is 5 times weaker than hydrogen bond, and a dipole-dipole is only 1% as strong as a covalent bond. So that's a vast difference. So make sure you don't think that they're even close to the strength of covalent bonds or ionic bonds. And if you can't remember, ionic bonds have an associated lattice energy, which is usually very large, and covalent bonds have an associated bond association energy, which is very strong. So IMFs do not even compare to those strengths. London dispersion is the weakest of all, and there's my note again, it is present in all molecules. The couple of interesting parts here, you need to be thinking about the Lewis dot structure for some of these, because you need to understand that the London dispersion is caused by a temporary dipole moment. It's a moment where there's an unsymmetrical arrangement of electrons around the molecule, so it's going to create a short-lived dipole moment. So if I'm talking about a helium atom, if the 2 electrons that it has are on the top and bottom, and then all of a sudden the electrons shift, and they're both on the bottom, well, all of a sudden we've got a partial negative end and a partial positive end. So that's as simple as it can get. It's just the shifting of electrons around. If you have more electrons, then you're more likely to shift your electrons around. The electrons are more likely to become distorted in a region where one has this high negative charge, and the other end of the molecule or other side of the molecule would have a low negative charge, meaning a more positive. So we call this high polarizability. It means that you have a large electron cloud that can be distorted. Couple more things here. The polarizability is related to the molar mass, and I just talked about how if we had more electrons, it was more likely to polarize. But molar mass does usually correlate with more electrons. So if you are simply trying to do a quick calculations, it's easier to calculate the molar mass of a compound versus count if it's electrons sometimes. Second one is the surface to surface touching or contact between 2 atoms or molecules. So if you are able to become stacked on other molecules in a flat manner, then your surface to surface contact is going to be higher. So flat molecules can stack, which would increase their London dispersion forces, versus really crooked ones. They don't stack as well, and they don't touch as well. So I can see my zigzag pattern does not stack as well. Low London dispersion. So we'll do some examples with this one as well. These induced dipoles, another name for induced dipole is a temporary dipole, which we also call London dispersion factors. Here's a quick example of this. So we have N-pentane, which is our linear or straight chain hydrocarbon versus a hydrocarbon that is not straight chain. It's called branched hydrocarbons take on a different shape. This one kind of looks tetrahedral. It's called neopentane. As you are using intermolecular forces to describe the physical properties, this is a big point. Physical properties are described from the strengths of the IMFs or interparticle attractions. Then a lot of times you might have to consider the same compound but an isomer of it. So these are isomers. It's the same chemical formula but a different structure, a totally different structure in this case. So the flat straight chain isomer is able to have a flat contact with one another and has a larger interaction of its surface area versus this small compact one which has a very small area to touch the other molecule, limiting the amount of attraction it can feel, which would therefore lead to different physical properties than the linear one, the straight chain. So all in all, if you have less contact, you attract less, which means that it's easier to pull you apart from your neighbor. If it's easier to pull you apart, then you have a lower boiling point. So branched chains have lower boiling points than straight chains. And looking at data, which is AP exam's kind of new big thing, if you can determine the relative IMFs felt, then you can also track or graph boiling point, melting point, vapor pressure, etc. So looking at this example, N-pentane lies down here, you can see that in accordance with increased molar mass, you have increased boiling point. Well, this is simply because as you increase the molar mass, you're contributing more electrons. More electrons are more polarizable. And these are all straight chains, so these straight chains are able to contact one another in a linear flat fashion. So nonane is going to have the highest boiling point here. If you were trying to figure out where the boiling point of neopentane laid was on the graph, we already said that branched ones have lower boiling points, so neo is going to be down here someplace. We don't have to tell exactly where, we just have to understand that it's less. Even though that it's the same molar mass, oh, let me graph that a little bit better. Even though it's the same molar mass, let's go right here, it's going to have a lower boiling point. So when we're tracking it over here, it's going to have, N-pentane's about a 39, neopentane might be a 20, so that's important. I'm going to make my but make sure that you're tracking as the same molar mass as well. Looking at this one, there's another data-derived decision. Dipole-dipole forces are going to exist in addition to the London dispersion forces whenever you have a permanent dipole. So when you're looking at this graph, you see that these colored regions are showing you areas where there are more electrons. The red one is a high electron density. So going from propane to dimethyl ether to ethylene oxide, acetaldehyde, and acetonitrile, and the dipole moments are listed down here, what do you notice? You can see that their average masses are about the same. They're 44, 45, this one's 41. But the biggest difference here is the boiling point is the highest whenever the dipole moment is the highest. So what you can say is that larger dipole moments yield stronger attractions, which is going to increase the boiling point because it takes a lot of energy to overcome such strong interactions with other molecules. So this is the last bit on IMFs. You already know Coulomb's law and you also know how to apply it, but you've never actually thought about the charges on these molecules. They don't have full charges, not a full +1, not a full -1, whatever it may be. They have partial charges, so partial positives and partial negatives. You can actually consider Coulomb's law in this application because these are charges, so let's just call them a small charge. However, when you're looking at the distance between molecules, there's going to be a larger distance that they're attracting over. So, in all, the Coulomb's charge, the Coulomb attraction is low, but it still is present. So you can use Coulomb's law to describe IMFs. And then hydrogen bonding is a relatively strong IMF because it has those larger charged poles, but it's still very weak compared to your other types of molecules. I'll go through the rest of this in just a minute.